complicated business. Right. So far, I just said all of these things, and that's for the recording. Never mind. So we carry on. Value function. So after doing all kind of manipulations, we arrive at this expression, which is true for the value function. And the Bellman equation for the value function expresses the value function just in terms of the immediate reward and the transition probabilities as a linear set of linear equations. And I don't think that I have enough space, so that it's going to be here. The Bellman equation looks like this. The value of policy pi at state S is equal to the expected value over the distribution induced over the actions, if you follow that policy from that state, times some quantity. The first part of it is the sum of the immediate reward plus gamma times all the future rewards that you could receive on expectation when you're arriving at some future state. And from that state on, since you're following the same policy, you expect to see the same value. So it's kind of like, intuitively, it's clear that this should hold. We're just trying to prove it. So this is a claim that this holds, and it should follow from just the definitions. And for the proof, we started off by this expression. We broke off the very first term, and then the remaining terms, and we were doing some manipulations. So let me just very quickly recap what was happening there. So if you break off the very first term, this is how it looks like. And then the remaining terms, they look like this. Correct. And then we started to manipulate things, and we expressed this just in terms of the policy and the immediate reward function. And it happened, so we could prove that this is the same as the sum. It's basically the expected value that you get if you're weighting the rewards with the probabilities assigned to actions by this policy pi. And of course, you're at state S. So that's the first part. And for the second part, we said that, OK, let's calculate this thing. And when we're calculating this thing, this expected value, then we just want to basically rely on the Markov property. So this, of course, expands into following the law of unconscious statistician. This is equal to the sum over ST and AT of the probability that the state happens to be ST and the action happens to be this little AT times the corresponding immediate reward. So at least we see the immediate reward there. Then we're expanding this term. And for this term, we just want to bring in the actions that were used in time step 0 and the state that you can land at. So you condition on these and multiply with the probability of these. And this probability, you can calculate it just pi A0 given S times the probability of seeing S1 given you start at S and then you take action A0. Okay? So we did that calculation the last time. So regarding the remaining conditional probability, if you just like look at it, we talked a lot about the Markov property. The Markov property says that the history doesn't matter if you have a state. Only the state matters. So this is part of the history. This happened before reaching this state. So you can actually just like remove that. I mean, here we have to also sum. So this probability here is equal to the sum over all S1 and A naught. Okay. So the Markov property just says that you can remove this. And if you think about it, it's like if you're at time 1 at state 1, what's the probability that you're going to be at time t at state st and you're going to take action at? That should be the same that you get under this different probability measure where the initial distribution is swapped to the distribution that puts a point mass at state 1. So here, this is state 1. So just this probability here should be the same as this. And then this takes care of this conditioning. Because now you are starting at state 1. How many more time steps do we have to go? Because we are starting at time step 1 instead of time step 0, we have t minus 1 time steps now. So I have to write as t minus 1. But of course, I want to still lock onto the probability of seeing state as t. So I need to write what's the probability under this initialization following policy pi to see state little st at time t minus 1 as the state and seeing the action at at time t minus 1. And lo and behold, if you're expanding these probabilities, you will see that they are the same. And this is what we started to write. And like, okay, we were just about to finish the last time, concluding that these two guys are the same. So now I'm not going to expand this for the sake of time. Just continue. And it's in the notes. So they are the same. So I can plug this here. And I have this. So I have to summarize everything. Okay, what is this? This is ST and AT. Okay. Going too quickly doesn't pay off. All right, so the first sum is over ST80. There is an inside sum as well. And eventually, I'm sure I will need to swap the sums. But anyways, that inside sum looks like this. And there is this probability. There's this other probability. Okay. And then there is that probability over there. The probability that you start at, the probability assigned to seeing at time t minus 1 state st and action at at the same time step times, okay, this line is very ambitious, st at. All right, line goes there. You have a lot to write. Okay, so we have these two sums, and they're finite sums, so they can be swapped no matter what. Okay, so that's good. So let's move the sum over A naught to be outside. And then let's follow with the sum over S1. And let's just move the corresponding terms before the other sums as early as possible to get some insight into what's going on. And so here we have the inside sum becomes ST80, and that just for this probability distribution where we are starting at state S1, following policy pi, looking at the probability of seeing ST at time t minus 1 and also seeing at the same time AT as the action times, okay, very ambitious, times the reward. Okay, so now if you look at this, what is that? That's the expected value of seeing of the reward, the immediate reward at time step t minus 1. Doesn't matter that these indices here are ST and AT. It could be like, I don't know, pink or green or anything. Like that index doesn't matter that it's t. We're still summing over all possible pairs of state action values. So this is just the expected value. At time t minus 1. This is what's important. Like that here you have this index t minus 1. So that goes there. All right. So that inside sum simplifies to this expectation. Okay. And now we can put everything together. If we put everything together, we have to plug in here. This expectation can be expressed with this value, this double sum and an expectation. Plug that in there. And then let's see what happens. So going back to that very first equation here, this. So YPS, VPS is equal to this sum times the immediate reward plus gamma times gamma t minus 1. And here I can collect this sum. So there is this sum, and there is, I don't know, this sum. So we can put them together. So that's just the same sum. I put the curly braces there so that I don't have to write that much. And I still have a sum over S1. And I'm going to swap this with the infinite sum, which you can also do. And okay, so before that, so this probability can go here. And the infinite sum all right. So what do we see here? Index goes from 1, but then it's shifted back by 1. So that's the same thing as index goes by 0, and there is no shifting back. So the shifting back is this t minus 1. So if this was not there, so that's the same as like t is greater than or equal to 0, there is no minus 1 here. No minus 1 there, no minus 1 there. Same expression. And what is that? Data S1. Right? So I'm inheriting that from here. So we calculated that that's under the probability distribution where the initial state distribution is S1. So what is this infinite sum? Is it familiar? Do we have it some form somewhere on the board? Yeah, it's exactly like this, except that instead of S here, we have S1. And so That means that this is V pi at S1. Okay. This is V pi at S1, and that's what we needed to prove, right? So that's the same thing as what we have here on the top, except that here, this is not called A naught, and this is not called S prime, but this is called S1. And yeah, in our case, it's called A naught, but that doesn't matter. Okay. All right, so finally, we're done with one proof. Okay. So what's the summary of all of this? So intuitively speaking, when you make a step, you arrive at a state. The future under this memoryless policies basically looks the same as if you didn't have any past. You're at that state 1, and the future total expected reward that you have at that state is just the value given by the value function. You have to count for arriving at that state, so that's the transition probability, and you have to count for what is the probability of taking the underlying action that will lead to that state or not lead to that state. So that's the probability distribution used in pi. All right, any questions for this? Okay. Is it clear what we were trying to do? We're trying to prove that holds, and we were just going through some calculations, some algebra, following rules, and we found that it's actually true. Okay. Good. So let's go on to the next topic for today, which is the Bellman optimality equation. I think this could be useful, except maybe this is not going to be needed. So the Bellman optimality equation is concerned with what? You read about it. What is it concerned with? What's the name of the thing? It's in the name, Bellman optimality equation. What is this an equation for? How is that thing called? Yeah, V star. Yeah, that was the symbol that was used, but what's the name for that? Don't remember? It's called optimality equation because that's for the optimal value function. Okay. Remember? V star, optimal value function. So what's the definition of the optimal value function? We denote it by V star, but okay, that's just a convention. So the V function also maps states to real numbers. How is it defined? What's the value that V star takes at state S in words? It's the optimal value. It's the best possible value that you can get if you follow some policy from that state. Okay, I want you to be brave. It's okay to, I say silly things. You should also say silly things. And you're not saying silly things. I'm saying silly things. Okay, anyway, so there is a little change here. You said max, I'm saying soup. What the heck is the soup? the supremum, we're over the real numbers. If you have a set, this is the notation for this is that like for every possible policy, you get a value. It's a real number. You can collect that into a set. No one knows whether that set is open or closed. It could be that it's like an open interval. It's like goes from here to there. Or it could have some much more complicated structure, but we don't know whether the maximum value of that set exists, right? Like for an open interval, there is no maximum value for the open interval. But we have a solution for that. And that's this notation soup. The soup just says, close that interval, then take the max. Okay? So if it was an interval, you would just close it, you take the largest value. That's a notation for soup. It's like a mathematical, important mathematical gimmick so that we can get away with not being bothered with open intervals and whatnot. We can just still think about largest possible value. It's the least upper bound. Huh? We don't know. We don't want to be bothered by proving that it's closed or not. And that's why, lazily, we just write soup. Maybe it's closed. Actually, it is closed. I know. But I can't really write it because I haven't proved it. I could only write it if I proved it. Okay. But you have seen this. It's calculus, right? So like in calculus, you talk about properties of real numbers, and then soup is just like one of these things. It's like, the good thing about it is that it does exist. Okay, if this set is infinite, then it's like, or like it has arbitrary large values, then that will be infinite, which is not our case. We talked about that the largest possible value that you can get is R max divided by 1 minus gamma, right? So in our case, this is a finite value. This is a well-defined function. So this is called the optimal value function. And here, I took the supremum or all possible policies. So another solution to our problem that we don't know whether a set is open or closed could be that we just have a finite set of policies. And then clearly the maximum value of amongst finitely many one, it exists. That would be a solution. But we don't have that because we have all these probabilities around. So even if you only consider memoryless policies, you already have infinitely many policies, uncountably many of them. So anyway, so that's the thing. But here, I'm allowing any policy. So that's a deviation from the book. My value could be higher than the book's value because the book just says, use memoryless policies. But we don't know. Maybe you're going to lose something if you lose memoryless policies. I'm allowing any policy. It's OK. We will still get everything. And we get the benefit that we can show that there will be no advantage of using history-dependent policies in terms of whether they could generate more value than the memoryless policies. All right. So finally, what's the Bellman optimality equation? So it's going to be an equation for V star. It's going to be very similar to the Bellman equation for policy evaluation that was stated just on the board. I just got rid of it. I don't know why, but maybe it would have been useful. Anyways, without further ado, can you help me to write this? So I want to express V star. It's similar to the previous equation. The previous equation, we started writing V pi s is equal to something, something. And then on the right-hand side, we also saw V pi values. So like on both sides of the equation, you have the value function appearing. It's going to be very similar to that. So what do I write next? Equals, what comes next? If we had a policy, we were summing over all actions and what probability the action is taken under the policy. But here, there's no policy yet. It's just a value function. So what do we replace that sum with? we're talking about large values. Should do something with the actions, but what? Exactly. Since we have finitely many actions, now it is safe to write max. Good. Just take the max over the actions. Okay. And then continue as with the same the previous equation, where we had the immediate reward plus gamma times is expected value. What to write here? What should I multiply that probability with? Any guesses? Yeah, which is right, V star S prime. So it has the same structure as the other equation. What is the difference? It's the max. We have a max. We are not averaging over, a distribution because we just go for the best possible value. So the intuition is that, well, what's the best possible value that you could get? Well, if I were to choose that policy, I would choose a policy that's maximizing the value. Then there is a question of what to put there. And then you can take a leap and then just assume that from this point on, you're going to act optimally. We don't know how yet, but okay. Then you're going to get this value. And if that is true, then this equation should hold. So intuitively, it kind of makes sense. All right. We want to prove this. This is the first time I call something a theorem. This is a theorem that this holds for every S. So it's notice that this is an equation. It's a system of equations. And V star appears on both sides. We have not the faintest clue at this moment. Okay, you already read about that, how to approximately solve this equation. But it looks complicated because there is this max. So we can't just rearrange and then use linear techniques to express V star. You have to do something else. We'll have good methods, that's DP methods, to address this problem, but not yet. So at the moment, we just want to show that this holds. Okay, so the proof is going to have two parts. But for me to reduce the amount of writing that I need to do, I'm going to introduce some function. So this function is going to be very, very useful. It takes some element of R to the S. So that's like a value function for every state. You have a value. And it returns the same thing. And what this does is that if you have some F that is in RS, okay, so that's you have a value for every S, then this thing, if you apply it to F, it's going to return a new function. So what's the value that function takes? I'm defining it. So this is the definition. This is going to be just this right-hand side. Okay? This is just a shorthand notation so that I don't have to write that much. But it will also be very useful. All right? So the trick here is that T applied to F is going to be this function G, which when evaluated at some state S is going to take on this value. And here is the dependence on F. So whatever F you plugged in kind of spits out some values, one for every state. Okay? This is called, all right, so functions that are acting on the top of functions. Well, we talked about functions, vectors, they're kind of the same. So you can think about that, okay, this is a function acting on the top of vectors. So these are sometimes called operators in mathematics. And this is the terminology that we're going to use, but it's just a function, maybe on the top of functions. If you did any functional programming, even Python, it has it, right? You can plug in a function into a function, it returns a function like that. That's no problem. This is doing that. Just a math notation for that. And you can also think that this f here is just a vector. And so you can just like take a vector, return a vector. We're all good. Okay. So the terminology shouldn't scare you. Like there is nothing behind someone calling a function an operator. There is no thought there. It's just that maybe, in programming as well, you want to know that you have a higher order function. This is a higher order function. You call it operator because higher order function is a mouthful. All right. Oh. Since writing these parentheses is just too much effort, we're not going to do that. Okay, that can cause further confusion, but you should think about that if you have an operator, it has the highest order priority of all the other operations, okay? So instead of TF, I'm just going to write T apply to F. It's like as if a matrix multiplies something, but it's not really a matrix because this is also nonlinear. So it's like F was a vector, then the result of this operation is not linear. Still, we write the same. It just removes some clutter because otherwise we would sink in the sea of parentheses. Okay, and with that, this can just be written as like this, TF at S, right? So TF, that's a function. You can evaluate it at S. I put these parentheses here because otherwise it's unclear whether this is binding here or what. The binding is clear. First you apply T to F, and then you evaluate that function. So this way there is no confusion. Okay, so the Bellman optimality equation with this notation just looks like this. Much, much easier to write, okay? And so the proof is going to boil down to two steps. Step number one. I don't know which step I'm going to prove first. I just do one. V star is less than or equal to TV star. Step number two. V star is, what do you expect if you write? Greater than or equal to TV star. That's right. You guys it right. Good. Okay. So let's get on at least to one of these steps. Probably can't finish both. I think I'm going to do step one. Let pi be an arbitrary policy. Fix pi arbitrary. No, any pi. Any pi. Okay. It has a value function. We define it. And this value function, this is what I'm not going to prove because we don't have that much time, but it's in the notes. It satisfies a Bellman equation very similar to the Bellman equation we had with some changes. How does it look like? So V pi s. So at time step 0, policy has this pi 0 component, which assigns probabilities to all the actions. So we're going to have the sum over all the actions, and then have to use the probability assigned to these actions by this policy. So this memoryless or memory-based policy or history-based policy has the sequence of like, what do you do in time step t? And then that can depend on the history. Time step 0, you do something. It looks like it's a memoryless policy at that time. And you get the immediate reward plus global times sum over all possible next states of t s prime given as a. And here, there is something here that we have to talk about, a function that assigns to every possible state some value. I denote it by W pi. And that's like a value function because that's like the future total discounted reward upon arriving at S prime. How much is that? Given that previously we started at S, took action A, maybe have seen some, like that doesn't matter what reward we've seen, that's integrated out, and we arrive at state S prime. But if you think about it, like if you have this memory-based policy, once you fix that you arrive at state S prime, it is just another policy. Now you're applying the policy that is the result of seeing some history. That history is fixed, but the rest is the same. It's like, okay, like what are the action distributions for the future steps? It's a policy. So you get a value function there for some other policy. I'm not using V because then I would need to name this other policy that's complicated. I'm just saying, okay, it's a W. I call this the W function. The W function is also a value function for some policy. That's the only important thing that we need to know. Okay, so it satisfies this equality. And since W pi is a value function for some policy, the value that it takes at S prime is upper bounded by V star at S prime, because that's the best possible value that you can get. Okay, so plug this in. Yeah.
Why do we write the pi with W?
W itself hides this history that you started at state, took action A, and you arrived at state S prime. Because then this policy changes. It's kind of, you have to shift the indices of the policies. You have to fix the history. You can formally write what the policy is going to be. So this is a value function for a policy that depends on what this history was. Okay? Yeah, this pi. Like from this pi, you have a whole sequence of things that you want to do in the future. You make one step. You still have a whole sequence of things that you need to do from step 1 on, given some history. That's also a policy. The value of that policy is what I'm writing here. Maybe I'd show it. Like you're at state S. You're taking, I don't know, action A, making a transition to S prime. And you had a policy. It was this whole sequence of pi naught, pi 1, and so on and so forth. Here, you already consumed one time step. So you have to, like when you continue from here, the new policy is going to start with pi 1. Right? Because that's for time step 1. And then there is all the remaining steps. You still carry that with yourself. But it's also specialized that we already took this step because these are history-dependent policies. They take into account the history. So they can do different things depending on what happened in the past. You can arrive to S prime by taking a different action A prime. If that is happening, it's a different thing that you are going to get. Right? Okay. It's the details are in the notes. Now you just have to maybe trust me that this W is also a value function for some policy. It's for history, some history-dependent policy. I think that if I write it down, like in the notes, you will see that, like, okay, this is well defined. This is okay. It's derived from the policy that we started from, but it cannot be the same because this is the policy that you will follow from step 1, and this includes step 0 too. And so it just basically the same, but not the same. Right? Just derived from that. Okay. All right. So after we are done with it, not equal, greater than equal. So, important thing. So what I'm doing here is that I concluded the W pi S prime is upper bounded by this value. Since it's upper bounded by this value, I can use this value and I get an upper bound for this whole expression. Why? Because these are non-negative, right? Like if there was some negative numbers, that wouldn't work, but these numbers here that are multiplying this value, they are non-negative, right? So I get something larger. If I have some value, a non-negative value, multiplying some value, and the second value is replaced with something larger, I get something larger as the product. Okay. So V star at S prime. Okay. So now we have that no matter what the policy was, its value is less than equal to what's here. That's T applied to V star at S. Is less than equal to T applied to V star at S. Take the supremum over both sides over the policies. Sup over pi in pi. So you have a collection of values. They're all upper bounded by TV star at S. The largest possible value that you could see in that collection is also upper bounded by TV star at S. So from this, it follows that V star at S, which is the supremum over all possible policies of V pi, at S, is upper bounded by TV star at S. And so with that, we are done with this. Because this holds for every S. Less than equal?
Like, what is it being compared to?
Oh, the previous. Okay, so this was a side note. Okay, I'm just calculating here things, and then sometimes I do have side notes. Sorry about that. Yeah, this was just like a side note that we know that W pi is upper bounded by V star. So we're gonna plug in the values of V star, and I'm continuing what I was writing before. So now this sum is upper bounded by this. Okay. Yeah, that's an excellent question because I can totally see how all this writing can get really confusing. But it shouldn't be. So if anything feels off, yeah, stop me. All right. Okay. So I don't think that in the remaining 1 minute, I will be able to do the other part, but the other part is not super hard either. We'll get to that, and it's going to be fun. We'll do the DP methods in the next class. V subscript star? Okay, and I'm using upper star. Okay, subscript, upper script is the same. Huh? R? I can't hear you anymore.